Welcome to the lecture series on CFD, Part 2. This is lecture 32b on boundary conditions for Reynolds-averaged Navier-Stokes equations. This lecture is devoted to some details related to implementation of typical boundary conditions at an inlet, outlet, symmetry plane, or wall boundary when solving the Reynolds-averaged Navier-Stokes equations. The problem is that the exact conditions at these boundaries are either not known or cannot be imposed in the exact form for various reasons. This is especially true for wall boundaries, and because of their great importance in turbulent flows, the largest part of the lecture is devoted to walls. Special attention is paid to the so-called logarithmic law of the wall and wall functions, which are used in simulations of flows at high Reynolds numbers. Periodic boundary conditions, which are often used to simulate fully developed flows, are also described. At inlet boundaries, in addition to velocities, turbulence model variables k and epsilon or k and omega need to be prescribed. They are usually not precisely known, in which case they need to be guessed. In laboratories, like wind tunnels, cavitation tunnels, or towing tanks, turbulence intensity may be known. It is defined as the root mean square of velocity fluctuation in flow direction divided by the mean velocity, as given by this expression. Here, u with over bar is the mean velocity in flow direction, and u prime is its fluctuation. Assuming that fluctuations are, on average, the same in all directions, as indicated by this expression, one can estimate the kinetic energy of turbulence as 1.5 times turbulence intensity squared times mean velocity squared. Estimating dissipation rate epsilon at inlet boundaries is more complicated. If the mean velocity and the main Reynolds stress component are known, one can estimate epsilon as given by this expression. Unfortunately, in most cases, neither the Reynolds stress nor the mean velocity profile at inlet is known. Near a wall, one can assume that the length scale of turbulence L varies linearly with distance from wall n as L equal 2.5 n. If turbulent kinetic energy is known, one can then estimate epsilon as k to the power 3/2 divided by L. Further away from the wall, the length scale does not vary much. It certainly cannot be larger than a fraction of the channel width, but how large the fraction is depends on the upstream geometry and flow conditions. In wind and cavitation tunnels, the length scale of turbulence depends on the size of openings in screens upstream of the nozzle and also nozzle parameters. When there is no detailed information about turbulence at inlet, the usual practice is to specify the turbulence intensity and viscosity ratio. Here is an example with specified turbulent intensity and turbulent viscosity ratio. Turbulence intensity is set to 1%, that is IT equals 0.01. Turbulent viscosity ratio is set to 10, that is turbulent viscosity mu T equal 10 times fluid viscosity mu. The mean velocity was set to 6 meters per second and fluid density is 1000 kg per cubic meter. Dynamic viscosity of fluid is mu equals 0.001 Pascal seconds. These are the properties of water. With this data, we can estimate turbulent kinetic energy according to the expression at the end of slide 4, k equal 1.5 times IT squared times u squared equals 0.0054. From the prescribed turbulent viscosity ratio and the specified fluid viscosity, we obtain mu T equals 0.01. We can now use the definition of turbulent viscosity in K epsilon turbulence models to compute the dissipation rate. Epsilon equal rho C mu K squared divided by mu T, resulting in 0.26244. When applying such approximations, it is advisable to compute the length scale using the approximation from slide 5, L equal K to the power 1.5 divided by epsilon, which gives in this case 0.0015 meters. We now need to check whether the length scale of 1.5 millimeter is reasonable for the given flow problem. Here is another example with specified turbulence intensity and length scale at inlet boundary. Turbulence intensity is set to 1%, that is IT is 0.01. Length scale of turbulence set to L equal 20 millimeters. Mean velocity U equals 6 meters per second. Fluid density rho equals 1000 kilogram per cubic meter, and dynamic viscosity of fluid mu equals 0.001 Pascal seconds. With this data, we can estimate turbulent kinetic energy according to the expression at the end of slide 4. K equal 1.5 IT squared U squared equals 0.0054. From the prescribed length scale of turbulence, we can estimate the dissipation rate epsilon using the approximation from slide 5. Epsilon equal K to the power of 3/2 divided by L equal 0.01984. From estimates of K and epsilon, we can compute the turbulent viscosity. Mu T equal density times C mu times K squared divided by epsilon equals 0.132. This leads to a turbulent viscosity ratio of 0.132 divided by 0.001 equals 132. We need to check whether the turbulent viscosity ratio of 132 is reasonable for the given flow problem. What is reasonable is problem dependent, related to upstream flow history, upstream geometry of the flow domain, cross-sectional area, etc. We now turn to boundary conditions at solid walls. If the wall is moving, its velocity is usually prescribed and no slip condition applies. Velocity variation immediately next to a wall in turbulent flows is linear with distance from wall. This zone is called viscous sublayer. Shear stress at the wall can be accurately computed if the grid resolves the linear velocity variation range. It equals fluid viscosity times derivative of the wall parallel velocity component in the wall normal direction. The problem is that the linear range extends over a very short distance from the wall, and to resolve it, an extremely small grid spacing in wall normal direction is needed. In addition, not all turbulence models are suitable for a resolved laminar sublayer, where viscous effects dominate. A special so-called low Reynolds number version is needed. Note that low here refers to the Reynolds number based on velocity fluctuation, which tends to zero with a vanishing distance from wall. Turbulent kinetic energy is zero at wall, because velocity fluctuations are zero there. However, its dissipation rate epsilon is not zero at walls, but the exact value is also not known a priori. Therefore, one must set epsilon at wall to an approximate value. Approximations given by these two expressions are often used. Velocity profile further away from wall is usually logarithmic, which is known as the so-called log law or law of the wall. This assumption is used to derive wall functions, which allow the use of a much coarser grid near wall than when the linear range is resolved. The first computational point and a few following ones must fall within the logarithmic zone. The normalized velocity distribution can be expressed as follows. U plus equal tangential velocity component divided by U tau, shear velocity equal 1 over kappa ln plus b. Here, Vt is the velocity component tangential to wall, and the overbar denotes the average value. The velocity is normalized by the shear velocity, defined as the square root of the ratio of wall shear stress and density. Kappa and b are empirical constants derived from experimental data. N plus is the dimensionless distance from wall. It looks like a Reynolds number defined with shear velocity u tau and wall distance n. Note that in literature, y is usually used instead of n to denote the distance from wall, which is the legacy of early two-dimensional studies. This plot shows the normalized near-wall velocity profile with the linear subrange up to n plus approximately 5, the buffer zone, and the logarithmic range started at about n plus equal 30. In addition to the assumed logarithmic variation of velocity in wall normal direction, two more assumptions are used to derive wall functions. The flow is assumed to be in local equilibrium, meaning that the rate of production of turbulent kinetic energy equals the rate of its dissipation, and the total shear stress, that is, the sum of viscous and turbulent contributions, is constant between wall and the first computational point. The variation of normalized production and dissipation of turbulent kinetic energy across wall boundary layer, channel width, or pipe radius obtained from DNS data at moderate Reynolds numbers is shown in this plot. We see that within log-law range, production and dissipation are practically equal for all three flows. We also see that normalized values of both quantities are equal for all three flows. Under the assumptions from slide 10, the following relation between shear velocity and turbulent kinetic energy holds. U tau equals C mu to the power of 1 quarter times square root of K. One can then derive an expression for wall shear stress in terms of velocity and turbulent kinetic energy at the first grid point P, given by this expression. Wall shear stress tau wall equal rho U tau squared, and then equal to this expression. Here, shear velocity squared was expressed as a product of two approximations, one stemming from the log law shown in slide 10 and one from this expression. The usual values of constants are given here. Kappa is called the von Karman constant. It was long believed that this constant is universal and valid for all turbulent boundary layers, but recent studies, both DNS and detailed experiments, show that it can be both lower and higher depending on the flow. The same is true for the constant B. This plot shows schematically the variation of wall parallel velocity component in wall normal direction across the first control volume next to the wall. To compute the wall shear stress directly, we would need to know the gradient directly at the wall, which is very high and not resolved by the grid. The velocity gradient at cell center is much lower and cannot be used to approximate the wall shear stress. Under the listed assumptions, the wall normal derivative of K is zero, which means that a zero diffusion flux for K applies at the wall. In the expression for the production of turbulent kinetic energy, the dominant term is the product of shear stress and the gradient of mean velocity in the wall normal direction. All other terms become negligible, and by assuming that both the shear stress and the gradient obtained from the log law are constant, the production of turbulent kinetic energy can be approximated in the near wall cell as follows. The derivative of the tangential velocity component in the wall normal direction can be approximated at cell center using the log law by the following expression. Under these assumptions, equation for epsilon does not have to be solved in the cell next to the wall. Epsilon can be fixed to the value given by this expression, which is obtained by assuming a linear variation of the length scale with wall distance L equal 2.5 n. This diagram shows velocity distribution in wall normal direction for turbulent flows in a pipe, a plane channel that is flow between parallel plates, and a boundary layer on a flat plate. The data was obtained from DNS of these flows at moderate Reynolds numbers. Note that all profiles overlap up to the end of the log range. It is important to note that as the Reynolds number increases, the log range extends to higher values of n plus or y plus. As shown in this diagram, the lower part of velocity profile is the same for all Reynolds numbers. But as the Reynolds number increases, the log range also increases. The data was obtained from DNS of plate channel flow at 4 different Reynolds numbers. The Reynolds number indicated in this plot is based on U tau, shear velocity. The highest value corresponds to bulk Reynolds number equal to 250,000, based on the mean velocity in the channel. This plot shows velocity profiles in a pipe at various Reynolds numbers derived from experiments performed at the University of Princeton, known as the superpipe experiments. These were the highest Reynolds numbers achieved so far in a laboratory. Reynolds number is defined with bulk velocity and pipe diameter, and the largest Reynolds number was 35 million. For all Reynolds numbers, the log law begins at about the same y plus, around 30. As the Reynolds number increases, the log law range extends to higher y plus values up to about 100,000 for the highest Reynolds number. This is important for the application of wall functions when computing flows at high Reynolds numbers in full scale. See slide 19. These two plots show grid lines and velocity vectors at cell centers in a channel flow at Reynolds number equal 500,000, computed using a low-array version of K-epsilon turbulence model on the left and using a standard version of the same model with wall function on the right. Instead of 3 cells with wall functions, we need 20 cells if we want to resolve the lambda near wall zone. The ratio becomes worse at higher Reynolds numbers. It is not only the number of cells that is problematic, it is also the aspect ratio that can cause trouble in simulations. Especially when the wall is curved, too thin cells are problematic because they become warped and the geometric centroid may not lie inside the cell. In complex geometries, we often have stagnation points or lines on walls where the velocity tends to zero. There are also recirculation zones with near-wall velocities much lower than elsewhere. It is therefore difficult to achieve a uniform distribution of I+ along all walls. Blended wall loads are used when the grid is not fine enough for low-rate treatment, that is, when Y+ is greater than 1, but the first grid point is not in the logarithmic range, that is, Y+ is less than 30. One example is the Reynolds law given by this expression. Here, B, C, and D are model parameters. A similar expression is also available for temperature. The implementation of this so-called all Y+ wall function is in SimCenter StarCCM Plus software available for all turbulence models. If possible, it is still advisable to use suitable mesh for either low-array approach with n+ or Y+ less than 2, or high-array with wall functions n+ or Y+ greater than 30 for a major part of wall surface. This plot shows a comparison of Reynolds' law with results from direct numerical simulations of turbulent flows in a channel or a pipe at different Reynolds numbers. Note that R8 tau is based on shear velocity u tau. We see that the agreement is not perfect, especially in the range between Y+ equal 5 and 50, but for many engineering applications, it is an acceptable compromise. At model scale, one can generate a grid with n+ approximately 1 with an acceptable number of cells. The aspect ratio of cells, length divided by thickness, should not be too large over a curved surface because of cell warpage. Up to 100 is acceptable and above 100 can be problematic. On plane walls, much higher values are acceptable. Even if all Y+ version of wall functions is used, one should avoid values of n+ in the range between 2 and 30 over a significant part of wall. One should either refine the grid to get n+ less than 2 or coarsen it to get n+ greater than 30. At full scale, that is, for high Reynolds numbers, wall functions are the only practicable choice because otherwise aspect ratio of cells near wall would be too high. At model scale, it is common to adapt the grid so that n+ is in the range between 50 and 100. At full scale, one can allow for larger values of n+ for next to wall cells, depending on Reynolds number. The higher the Reynolds number, the larger can n+ at the first cell near wall be. See slide 15. It is only important that several near wall cells fall into the log range. In turbulent flows, Reynolds numbers are usually high and disturbances from outlet boundary do not propagate far upstream. This is why at outlet all variables are usually extrapolated in the flow direction to boundary nodes. The simplest option is to set boundary values equal to the value at the center of the next to boundary control volume. Velocity component normal to boundary is corrected to ensure that the mass conservation is satisfied. It is important to set the outlet boundary far enough downstream of the region of interest and in particular far enough from recirculation zones. It is also desirable to have the outlet boundary be orthogonal to the flow direction. Sometimes pressure is specified at the outlet, almost always when the flow is compressible. Solutions of Reynolds-averaged Navier-Stokes equations may be symmetric, so symmetry conditions are often applied to reduce the computing effort. Symmetry condition implies zero gradient in the direction normal to boundary for all scalars and the velocity component parallel to symmetry plane. The velocity component normal to symmetry plane is set to 0 at the boundary, but its gradient is not 0. However, sometimes the flow is not symmetric even if the geometry and boundary conditions are. Imposing symmetry conditions enforces one possible solution which may not be stable, and the solution from the complete geometry may be different. Here are two examples. This plot shows the flow pattern and velocity distribution in a symmetric diffuser. The run solution is asymmetric and steady. Similar observations can be made in experiments. The asymmetric solution is more stable than the symmetric one. This plot shows the well-known vortex shedding behind a circular cylinder. Shown is the instantaneous vorticity from an unsteady run solution. If the simulation is performed in half of the flow domain with an imposed symmetry boundary condition, the flow would be steady without vortex shedding. Periodic boundary conditions can be applied at side boundaries or with an imposed pressure drop or flow rate, also at inlet and outlet boundaries. When computing fully developed flows in channels or pipes, it is sufficient to use two layers of control volumes in the flow direction. Because periodic condition is not unique, the solution domain should be at least as long as it is wide to impose the flow direction. With too short solution domain, convergence problems may be encountered and the velocity component in cross-flow direction may not be zero. This plot shows velocity vectors from a computation of fully developed channel flow with a sufficiently long solution domain. Only two layers of long control volumes are used. The other plot shows the results of computation for the same fully developed channel flow, but the solution domain is very short. Again, only two layers of cells were used, but they were 10 times shorter than in the other simulation. The convergence is worse with the shorter domain, and the maximum velocity is also different from the long domain. Here is a summary of this lecture. In many engineering applications, exact conditions at the inlet are not known, and engineers must make plausible approximations based on assumptions regarding turbulence intensity, its length scale, and the mean velocity profile. The outlet boundary is less critical. Extrapolation in the flow direction usually suffices. Both inlet and outlet boundaries should be placed sufficiently far away from the region of interest to minimize the influence of approximations made in boundary conditions on the result. Repeating the computation with varied conditions is advisable to assess the effect of variations on solutions. If possible, the grid should resolve the boundary layer at walls down to y plus approximately 1. Otherwise, y plus greater than 30 is advisable for the application of all functions, even if all y plus version of all functions is used, which is helpful if locally low y plus cannot be avoided. Symmetry plane boundary conditions should be used with care because the solutions of Run's equations for the complete geometry are often not symmetric.